Hi guys, welcome back to another video. Today we'll be going over capacitors and using the capacitor equation Q is equal to VC, and just really combining it with Ohm's law and just having all sorts of fun combining these two equations, looking at different equations, having a conceptual understanding of how things are related to the other. Hope you're excited. Let's get into it. So on the whiteboard right now are two equations that we use to equate to circuits. So we have our classic Ohm's law that we're introduced to in Physics 1, AP Physics 1, and we have our capacitor equation. So Q in this case represents the amount of charge on the capacitor, on one plate of the capacitor. C is the capacitance, so how much charge can it hold on the capacitor, and V is the voltage. And Ohm's law, as we all know, is V is for voltage, I is for current, and R is for resistance in the system, in the circuit. So if you draw a basic circuit, so here's your battery, this is your minus, this is your positive. So you have resistance maybe right here, and then this is how you draw a capacitor. Relatively straightforward. This is how you draw a capacitor. So what capacitor really is as charge flows through the system, as charge flows through the system, it basically has, if you enlarge in this image right here, it has two metallic plates and it's separated by empty space here. A zone where the electron from this side that is going through the circuit cannot move through. So technically, charge will pile up on this side of the capacitor and will accumulate charge over time, essentially blocking off part of the circuit. And at one point, we have all these charges of, let's say, Q on this side, that at that point, all these electric forces, all these repulsion forces are going to overwhelm the oncoming charges and start repelling them backwards. So what you get is a discharge of the capacitor. And so the really cool thing is that essentially electricity starts flowing backwards. The other way around, I should probably say, because charge goes from negative to positive. But let's go more into the math, because this may be a lot conceptual. This is essentially what a capacitor is, but let's get our hands dirty with some math. So first thing we can do is another idea that I haven't included yet is that the derivative of the charge over the derivative of the time is equal to the current. Or if it's a discharge relationship, it's be negative. Let's go over discharge a little bit of the capacitor and how it works. So once again, you have a very simple capacitor. We have the battery, the capacitor, and the resistor. Let's say. So let's say we let this charge flow, and we fill up the capacitor with charge. The cool thing that can happen here is that since this capacitor is filled up with charge, if we get rid of this battery and just make a circuit by itself, we will see all the charge that has been accumulated on this will just start flowing through the circuit, essentially discharging the capacitor. So how do we model this through math? So with the given ideas we have right now, what if we just take our basic equation and take it in terms of time? So dq dt is equal to C. C is really just a constant. It's capacitance. We can treat it as a constant. We can look at a change in capacitance, but in this context right now, it is not relevant. Is equal to C dV dt. So we see how dq dt can be related to negative current. And so ultimately we get I is equal to C dV dt negative. So we can see as the change in current, the change in voltage increases, there will be a decrease in the current and vice versa. So now what happens if we just plug in Ohm's law into the capacitance equation? So you can write this as Q is equal to C times, now we plug it in, RI. Now this is going to be interesting because when we take the derivative of time on both sides, we are assuming constant capacitance and constant resistance throughout this circuit. Di dt, which is actually very interesting because when you write the full equation out, we have essentially a separable equation, which I will solve towards the end of this video. Now let's take back this equation right here, and what if you plug in I is equal to V over R, so if you plug that in, so V over R is equal to negative C dV dt. There we go, we have one more equation that actually relates a certain quantity and in terms of that change in a quantity. And these two look awfully similar. Okay, so now let's look at this equation specifically right here. So when we try to solve this through a separable equation, so we're going to try to get the I on the same side as dt and everything else on the other side. So when we go through this process, we will end up with di over I as we divide that over and divide these two constants over and multiply dt over. We will end up with negative c r over 1 over negative cr times dt. Now, if we take the integral of both sides, important thing to note here is that if we want to not end up with a constant at the end, we will write this as I initial, I final, and 0 to t. And we will solve this out, ln of I final over I initial is equal to t over negative cr. Okay. So from here, it's important to note that if we did not have bounds here, we could have just took the integral, have ln of I is equal to t over negative cr plus c. And then if we were given a certain point, let's say as the capacitor discharges, our current is this, our time is this, what is let's say voltage, we could solve out this equation, find out overall what this is, and then relate it back to another equation that we can derive. But let's just focus on when we have definite bounds. So we don't have a plus c, we raise both sides to e, so we have I f over I initial is equal to e to the negative t over cr, and that would be our equation. But to finish it off, we have I final is equal to I initial times e to negative t over cr. And that allows us to be like, okay, so if we have a problem that gives us the resistance, capacitance, time, and the initial current through this equation, we could find other, like, what the current final is, or vice versa with any of those other constants. And as we see, I and di dt in this equation basically had the exact same, except for v, sorry, this should be dv dt, right here. And from here, we can literally just deduce that this, or v final, will be equal to v initial e to negative t over cr through the same derivation. So overall, that is it. We went over concepts of how really a capacitor works, why it works. Overall, this was really just us having fun with the capacitance equation, ohms, and just playing around with the variables, how we can make them interchangeable, and finding some pretty cool relations. Keep in mind that these two relations will be in terms of the discharge, not as the charge, because as time goes on here, the current will will increase because we will end up with I final, I initial over E to the T over CR. So this will increase. Apologies. The current final will actually decrease because we'll have this, and as the denominator gets bigger, this overall term right here will approach 0, and therefore I final in the long run, the final current after the discharge will approach 0. Thank you for watching. I hope you learned something, and I hope you enjoyed it.